Hello everyone. In today's recitation, we do a review of general topics and concepts that we covered in Module 1. This will be a good preparation for you in the week before the final exam for Module 1. If you remember, what we started with was the idea that in fluid mechanics, unlike other fields that you have probably seen problems before, such as dynamics or solid mechanics, we have a huge number of elements. In solid mechanics or dynamics, we usually are concerned only with a few limited number of elements, and it's relatively easy to follow their trajectory in a space with time. That approach, following the trajectory of, for example, a single object with a fixed identity in a space with time, is what we described as Lagrangian approach or description. You can follow the position of a fluid element as it moves in the space with time. Its position x as a vector is a function of time, and to identify our particle, to label it by a name, we give it the name x0, which means at time 0 it was in position x0. That's just a label. It doesn't change. For a fixed particle with fixed identity, this label doesn't change. It's like my name. Now, this approach, as I said, is very useful when we are only looking at a few limited number of particles. Unfortunately, or maybe fortunately, in fluid mechanics, we have the abundance of number of particles and fluid elements that you can imagine. At each instant of time, your field is full of millions and billions of fluid elements that are moving. You can see that Lagrangian description may not be the best approach. The alternative approach to describe quantities and parameters in your problem is what we call the Eulerian description. Eulerian description deals with a field. So you have a field, for example. If it's a 2D problem, it's an XY Cartesian coordinate system like here. And for each point in this field, at position, for example, x, and at a given time t, you can measure the property of interest. For example, the temperature distribution in this room. That's a flow field, that's a temperature field, and we are describing it in an Eulerian description. You can see these two should be connected, because if I have the temperature field of this room, I know that the temperature of the particle that sits at this position at a given time should be described from Eulerian description by looking at that coordinate system and at that specific instant of time. But at the same time, I know that there's a difference. The moment this particle wants to move to a new position based on its own velocity, it may experience a different rate of change in temperature compared to a similar particle that comes here at a different time and moves to a different position. So you can see that although these two are really equivalent and very much similar descriptions of the same thing, a temperature field, because of this difference of perspective, the way we need to calculate the rates and connect them together is significantly different. We learned that there's a nice way to connect these two together. If we sit on a particle and look at the rate, for example, of the change in temperature of that particle with time in the Lagrangian description, which I'm showing with the magenta color, that is what we wrote down as capital D, or total derivative of t divided by dt. This is the Lagrangian description, which means that I am following the fluid element. But we saw that this can be easily connected to the measurements that we are doing in a temperature field, which is the Eulerian description, and is connected to the Eulerian description of the temperature field by two different terms. The first term is at a fixed point. We take the derivative of temperature with respect to time. And the second term is velocity of the fluid element multiplied to the grad or nabla operator acting on the temperature. And these two terms had different natures. This is what we call transient derivative and shows the transient nature of the flow field. And this is what we call the advective term, which shows the advection nature of the flow field. In other words, if you're a fluid particle, there are two ways you can change your temperature. You can sit on the fixed position and don't move at all, have zero velocity, which tells you that you don't have any advective term, but just change your temperature based on some internal metabolism in your body. For example, in this room, I can stand still in this point, and if I have had some spicy food before coming here, that the spicy food burning and internal metabolism in my body is going to raise my temperature without me moving at all. But what if I don't have that internal metabolism, and in this room just move from a cold spot in the room, which is here, for example, to a warm spot which is close to the heater? then I will have a change in my temperature due to my travel in the room, which is the advective term. Now, you can have both together. You can have an internal metabolism burning calories and giving you extra energy and calorie that goes to a raise of temperature in your body. And also at the same time, you can be moving around in a flow field or a temperature field that gives you different feelings of temperature as you are moving. The rate at which you are moving in the field is captured by velocity and will tell you whether you feel an increase or decrease in the temperature that you experience. Now, connecting these two together for a scalar such as temperature is relatively easy to understand and think of. But most importantly, we showed that this concept becomes very important in fluid mechanics when we apply it on a vector such as velocity. So the derivative of velocity of a particle or fluid element with respect to time, which if you like to think about it, this is equal to acceleration of the fluid element, or A, is nothing other than, so this is a Lagrangian concept, is nothing other than take the transient derivative of the velocity with time at a fixed position. So this is a vector field. It's not anymore a scalar field. It's a vector field that at each instant of time, at each position x, we know it and we have recorded it. And the second part, which is which is not transient anymore, is the advective part, is the operator of Nabla or Grad when velocity is dotted to it, acting on the velocity vector itself. And if you remember, we showed that when you expand this, it becomes dv over dt plus terms such as vx d over dx plus vy d over dy plus vz d over dz. The summation of these three operators all acting on the velocity vector. If you remember, in the initial week of the class or module 1 that we covered, we showed how we can actually use kinematics, given kinematics in terms of velocity field, to connect it to the acceleration of fluid particles that are moving in that velocity field. This is a very important concept. And again, we can see that you can have acceleration of a fluid element due to transient nature of the flow field. Or even if the flow is completely a steady state, which means this first term is 0, you can still have acceleration just due to the advection or the motion of the fluid elements from one region of lower momentum to another region of higher momentum.